So, hello everyone. My name is Ghareeb Falazi and I'm from the Institute of Architecture of Application Systems of the University of Stuttgart. And today I'd like to present to you a recent research we had at the Institute, which is entitled Modeling and Execution of Blockchain-Aware Business Processes. First, let me shortly introduce the agenda for my talk today. So first I'm going to talk about the motivation behind our approach, and then about a challenge that faces it, which is the durability or finality of blockchain transactions. Then I'm going to dig into some details of the approach, and the approach itself has two aspects. So blockchain access layer is an execution aspect, and blockchain-aware BPMN extension is a modeling aspect. And I'm going to talk about the entire system architecture as well. Finally, I'm going to give some conclusions. So what is the motivation behind our approach? Well, the approach is pretty simple. It revolves about the idea that blockchains are beneficial in situations that have multiple participants which want to operate together. So let's imagine some business partners who have a joint business model or business process, but these participants don't trust each other. So participants, for example, business partners with some conflicting business interests, and yet they still want to have this joint process. And the solution to this is either blockchains or a trusted third party. So if we want to have blockchains, then we have a new kind of business opportunities in the fields of supply chains, healthcare, finance. In these fields we see now an emerging usage of blockchain. This is on one hand. On the other hand, in these fields, business partners already have modeled their business processes using languages such as BPMN or people. And my approach, or our approach, is just to allow these existing business processes to communicate with the emerging blockchains. This sounds like an easy idea, but it faces a challenge. And this challenge is the durability of blockchain transactions. And in order to understand why we face a challenge here, let's first understand what blockchain transactions are. So blockchains in general manage or store some kind of a state. So Bitcoin, which is one blockchain system, stores accounts and their balances. Ethereum, on the other hand, which is another blockchain system, stores smart contracts and their local storages. Blockchain transactions are transformations of these states. So a Bitcoin transaction is a transfer of funds from one account to another, and an Ethereum transaction is an execution of a smart contract that changes its storage from one state to another. Well, these transactions have some inherent properties because of the underlying protocol, the blockchain protocol itself. And one of these properties is the durability of blockchain transactions. And to understand this specific property, let's take a look at this figure, which shows a simplified version of the life cycle of a blockchain transaction. So when one of the partners issues a transaction, a new transaction, it is in the created state, and it is broadcast to all participants in the network. And then these participants validate this transaction against a set of rules, and if it's valid, it becomes in the valid state. And now a subset of transactions, which we call miners, try to put all new transactions into what we call blocks. And the issue we face here is that we have many miners, and we need to determine which block generated by these miners is the actual truth, the actual block that would be appended to the blockchain. And in order to solve this issue, these miners all participate in a competition. This competition is just a mathematical puzzle. And the first miner who gets to solve this puzzle gets to put its version of the block at the end of the blockchain. And now if our transaction gets into one of these blocks and is appended to the blockchain, it is moved from the valid state into the mined state. However, even in the mined state, we have a risk to go back into the created state. And this risk is called forking of the blockchain. And I'm going to explain this in the next slide. But the idea that I want to have here is that we need to wait in the mind state, wait for additional blocks to be built on top, because only then we can be sure that the transaction is durably committed. And the reason is that forking, or the probability of forking, decreases with new blocks built on top. And now, what the hell is this forking? Which is the major issue of blockchains from the durability point of view. So let's take a look at this example here. This is one way forking could happen. So the world here is green because it represents all nodes, and it's green because all nodes can communicate together. And now let's assume that the blockchain now contains only a single block, A, and after some time an additional block is added, B, and after some time an additional block, C, is added. And now let's assume that some network partitioning happens. So the world now is separated into this blue section here and this red section. So we have basically two versions of the blockchain, a version visible by the blue nodes and a version visible by the red nodes. At this moment, these versions are the same. But after some time, the red set of nodes produce 2 blocks, while the blue set of nodes produce 4 blocks. And now if the partitioning is over and all nodes can communicate together, all nodes can tell that we have 2 versions of the blockchain. A version is, one of the versions is this and the other is that one. Which one of these is the truth? Well, the rules say that the longest chain is the truth. That's pretty simple. This means that this chain is the truth and these 2 blocks are forked or are orphaned. So what happens to the transactions which are in these 2 blocks? They move from the mined state to the created state. And then we face 2 options. One of which is going from the created state to the invalid state. This happens, for example, if we have a transaction here in the other set of nodes, which contradicts this one. So let's say I have in this transaction the information that I want to send all my money to Alice. And over there, we have a transaction that says I want to send all my money to Bob. And now because these set of blocks mean the truth or correspond to the truth, this means that the transaction that says I want to send my money to Bob is the truth, which contradicts with this one. So we had a transaction which was mined, and eventually it became invalid. On the other hand, if we don't have a contradicting transaction over there, this transaction moves from the created state to the valid state, and which can eventually become mined after some time. So the message I want to deliver here is that external applications or applications external to blockchain systems need to be aware of this life cycle of blockchain transactions, and more specifically be aware of such transitions, which make some mined transaction and invalid transaction. And our approach aims at providing this information to external applications at 2 levels. First at the execution level and then at the modeling level. So let's start with the execution level. At this level, we introduced a system, let's say, that we called blockchain access layer. And this is a unification layer that allows external applications to perform some operations on blockchain transactions while modeling the transitions or modeling the trade-offs possible when we want to deal with the durability. So what trade-offs are possible? Well, they are basic. We either want to be absolutely sure that a transaction is committed before we do something, or we want to operate as quickly as possible on blockchain transactions. And in order to do that, we had to measure the durability of transactions somehow. And and the most famous measure for that is this block confirmations. How many blocks are built on top of the current transaction? So yeah, this is a unification layer, and for all peer-to-peer protocols, you need to have some local instance of the protocol that executes it. So in this case here, we have, for example, if we want to communicate to the Ethereum protocol, which is one blockchain, And to the Bitcoin protocol, which is another blockchain, we have local nodes. So here we have an Ethereum node, here a Bitcoin node, and blockchain nodes in general expose some sort of an API. So here we have technology-specific APIs, Ethereum API and Bitcoin API. But here at the top we have a unification layer, and in order to unify these kinds of APIs, we have in the middle a layer of adapters. So this allows us to have here a technology agnostic layer, and furthermore it allows us to extend our approach when we want to support some other kind of blockchain. So we just add an additional adapter here. And finally, these operations here are asynchronous operations, because when we want to deal with blockchain transactions in general, this can take a lot of time. So, for example, in Bitcoin, if we want to be sure that a Bitcoin transaction is durably committed, we want to wait about 1 hour. And doing that synchronously is not a valid option. That's why we have an asynchronous API. So here is the set of basic operations we provide. I don't want to go into details. Of course, we can discuss them more on the poster session or in the paper. But all of these operations accept this parameter I talked about, block confirmations. And when we have a higher number here, this means that we want to be more sure that the transaction we are dealing with is durably committed. If we have a lower value here, we want to operate on this transaction as fast as possible. Now, let's move to the modeling level. So at the modeling level, we introduced a BPMN extension, which is called Blockchain Aware Modeling Extension, or BlockMe for short. This extension has the look and feel of BPMN. It contains a set of tasks and events, and it allows us to express exactly the trade-off I talked about, but visually. And what I found to be important is the ability to transform this extension into standard compliant BPMN2, which means that we don't need to have a specialized process engine to execute it. We can, but we don't have to. Okay, so I intend to explain some aspects of this extension through an example. So this is a pretty simple example. We have a shop, a web shop, for example, that wants to accept payments in Bitcoin, and afterwards operate on this payment. So to receive a Bitcoin transaction, we have this extension task, which is called receive transaction, and afterwards we want to operate some uncritical operations, like sending a confirmation back to the client that, okay, we received a transaction from you, and some critical operations, like sending the actual product to the client. So for these uncritical operations, we don't want the client to wait for too long, and that's why we have a property of this task, which says wait until with a value of 1. This means that I only want a single block confirmation before continuing, which means I only want to get into the state of mind and not wait anymore. So when the transaction just gets mined, the execution moves immediately to the uncritical operations. However, for the critical operations, I want to be sure, at least more sure, that the transaction is durably persistent. And that's why we introduced here an additional task, which is called ensure transaction state, with a value of wait until 12, which means that we want to wait for 12 block confirmations before we continue. Of course, in order to tell which transaction needs to be monitored by this task here, we pass this information from the previous task. And now during the wait, during this 12 confirmations, which are 2 hours in the case of Bitcoin, if we detect that the transaction is orphaned and invalidated, we can receive this information here on this, using this message catching event. And then perform some sort of compensation. In this case, we just terminate. We could send another message to the client that your transaction is not valid anymore. We won't send you any product. And now, when all of these operations are performed, we just terminate. Now, these are the set of all extension artifacts we introduced. Again, I don't want to go into details here. We can discuss that in the poster session. I just want to show that these extension artifacts are mapped one-to-one to the operations provided by the blockchain access layer. Okay, and now I mentioned before that these artifacts can be transformed into BPMN fragments. And I want to show one example of this transformation. More specifically, the transformation of the ensured transaction state task. So here we see the original example, and here we see the transformed one. The task is transformed into a sub-process, which contains a message-sending task and a message-receiving task. The message-sending task's role is to subscribe with the blockchain access layer, subscribe with the corresponding operation of the blockchain access layer, and it provides the address of the other task as a callback URL. We remember these operations are all asynchronous, so the results are sent back here. When they are sent back, when the blockchain access layer detects 12 block confirmations. Furthermore, we might face some correlation issues, and that's why we have some sort of a correlation ID that is sent from the first task to the second task. And again, the receiving of the event of invalidation of the transaction happens now on the boundary of the sub-process. And most transformations happen similarly. Okay, now this is the architecture, the whole architecture of the system. We have seen this part here before, and this part over there shows the developer or the modeler who first uses the extension to model some business process model, and then transforms it into standard compliant BPMN and deploys it to a standard process engine. And then during runtime, and according to the modeled BPMN, this process engine communicates with the blockchain access layer using subscriptions and unsubscriptions, and it receives callbacks from it. Okay, so to conclude, in this work we identified the issue of durability of blockchain transactions, and we proposed a two-level approach to allow external applications to deal with this problem. One at the execution level using the blockchain access layer, and one at the modeling level using the BlockMe extension. Okay. So I'll be happy to further discuss with you at the poster session. And yeah, thank you.
Thank you. Okay, if you have one quick question, you may. Yeah.
How hard is it to detect the orphans?
I couldn't hear you.
You talked about the orphans, that you have a partitioning, and then you have to decide if it fits, you can mix it or merge it, or you're not able to merge. How hard is it to detect that?
It's not so hard because it's a peer-to-peer protocol, so all peers receive all information. So if you just have a local peer, you can detect all events that happen in the blockchain. But only, of course, when the two partitions merge, when every node can communicate with the other, then it's not so difficult.